Yeah, sorry I started recording a little bit late, but welcome to the OpenStreetMap in Python workshop. I'm taking you through the process of logging into Jupyter Hub. And so here is the information of how to log on. Go to jupyter.edri.ucla.edu, do a multi-factor authentication with UCLA or USC, and launch a terminal window from within your Jupyter Hub. And this is what I want you to do within the terminal window, is to type in git clone. And then this is a bit of a lot to type, but please type this in as well. github.com/yohman/osm-workshop.git. If you are on my repo page, you can also copy that link here, or you can type it in. The command is git space clone space and then this URL, https://yohman/osm-workshop. Okay. Yeah, thank you. So the recordings will be posted, and I'll be sending a link to the recordings. In fact, not just mine, but all 4 workshops today will be recorded and sent to all registered users. So you will get an email likely tomorrow morning. Like I did today, I sent you all an email about yesterday's recording. So you will get an email regarding all the recordings. Okay, so far so good. Great. Let me know if you have succeeded with that. You should now see in your Jupyter Hub space, make this a little bigger, a folder, OSM-workshop. Can I see a thumbs up or some reaction that tells me that you guys, yeah? Oh, awesome. Wendy, Jessica, great. Zach, Peter, okay. Can you, oh, I see an unhappy face. Okay. See a lot of got it. Okay, I'll quickly go over it one more time. And if, so actually I'll need a little more information. Samantha, at what point are you not, are you having problems?
So I was able to log onto the Jupyter Hub and I see like this notebook list is empty, but I'm a bit confused on, I guess, how to copy and paste the code.
Oh, the terminal. Okay. Yeah, let me just quickly go over that again. So if you are inside the Jupyter notebook, launch a terminal window. That's the first thing. And then you need to type in this command, git clone, and then the URL to my repo. And I should just paste this in the,
Got it, thank you.
Yeah. And yeah, Craig, apologies in advance, but I don't think, Ben, correct me if I'm wrong, we've only set it up for UCLA and USC multi-factored logon, is that right?
That's correct. Or you could choose Google, but it would require that you have, it requires that you have the ucla.edu or the usc.edu email associated with it.
Okay.
I could try and set something up here quickly for Binder if you'd like me to try and go ahead and do that for these folks.
Right. Yeah. So yeah, sorry, Craig. The material is up, and you can actually download the notebook and launch it in your own kind of environment. And I'll explain the libraries that you have to install if you want to do that. But I'll go ahead with the workshop. All right, so we're all here. We see the OSM workshop. Click on that and launch the OpenStreetMap notebook here. And this should open a brand new tab with a whole bunch of what these are called cells within your Jupyter notebook. And we're going to run through our workshop as we go through this notebook. If you're new to Jupyter notebooks, the Jupyter notebook interface allows you to kind of mix regular text in what's called markdown language, which is similar to HTML, which is basically a form of narration and storytelling on the web. So if you just want to write a paragraph, a header, bullet points, like I'm doing here, these are called markdown cells. But what's intriguing about a Jupyter notebook is that you can also mix in what's called code cells. So you have narrative cells, markdown cells, and then you have interactive code cells. This is the new kind of wave in kind of narrative coding through these interfaces like Jupyter Notebooks. Google has their own thing, but Jupyter Notebooks is open source and it's widely used in academia. And it's great for workshops because I can cover a lot of instruction that has a lot of explanations about what's going on and interact with the code along with you. So we're using this interface. If you are new to Jupyter Notebooks, notice that you can highlight a cell by clicking on it, and it kind of creates a bounding box around it. And if it's a code cell, like this one all the way down here in 2.2, and you click inside the code cell, you see the cursor inside the code cell. If you want to run this cell, in other words, you're interacting with the code and you actually want to run this, you can click on the run button up here. That's method number 1 to run a cell. Or you can do a shift enter. Okay, I'll repeat that. Shift enter runs the cell so that it actually runs Python for you because the code that we're running is in Python. So I'm going to start kind of in presentation mode, but for you, I'm running the exact same notebook, but just going into presentation mode. So my screen might look slightly different from yours, but it's the exact same notebook. You will continue to work linearly downwards, but my notebook will be in presentation mode. So just to let you know, this session is being recorded, and let's get started with the material. All right, so OpenStreetMap, if you guys participated in yesterday's Mapathon, we're all by now familiar with the concept of OpenStreetMap. It's the world's largest wiki map. It's like the Wikipedia for maps. The beauty of OpenStreetMap is that you are the authors of it. And since most of you have already created an OpenStreetMap account, you can actually contribute towards OpenStreetMap to create the world map made by people like us. We are going to use this lab to learn how to manipulate or how to interact with OpenStreetMap data within a Jupyter notebook using Python. So there's a lot there. And since this is both an OpenStreetMap and a Python workshop, I'm going to cover a bunch of Python kind of introductory and some advanced commands. And at the same time, but we're also working with OpenStreetMap data. So we're kind of combining OpenStreetMap and Python. And eventually we're going to create some pretty compelling maps to share with each other. So what we're going to cover today is we're going to use a couple of Python libraries to download OpenStreetMap data. We're going to categorize the downloaded buildings because that's what we're downloading, our buildings by type. We're going to visualize the buildings on a map, and time permitting, we'll get into functions and then into loops. But I may not get to the function and the loops, which is a little bit more advanced Python concepts. But if we don't, know that all the material and explanations are within this notebook, and you can run it on your own if we run out of time. Okay. So I wanted to introduce to you the libraries that we're going to be using today. If you're new to Python, it's similar to R or other coding languages nowadays, that usually on the top of your code, you're going to import libraries and or modules. And what a module or a library is, it's a chunk of code that somebody else wrote that you're importing into your library that then allows you to use the functionalities that did not exist prior to you importing it. So for example, we're going to use these 4 libraries for this workshop. Pandas is perhaps the most utilized Python library in terms of data exploration. And Pandas allows you to import data. You can import CSV data, JSON data, any kind of data, and then you can read it in, manipulate it, clean it up, query it, filter it, and visualize it using Pandas. A GeoPandas is Pandas, but with the geo attached to it. So in addition to everything that Pandas, for the most part, can do, the GeoPandas library allows you to spatialize it. So if I go to the GeoPandas kind of help, well, this is kind of all the help structures, but you can actually come here and see that the GeoPandas library allows you to create maps like the one you're seeing on the screen right now. Through just a couple of lines of code, you can create, and this is a choropleth map with a legend and so forth. So these powerful libraries are available to us to use, to import, and then with just a few lines of code, in theory, you're able to visualize your data in a way that might advance your agenda, your research, whatnot. So that's the GeoPandas library. The library that we're going to use to interact with OpenStreetMaps is this one called OSM and GIS, OpenStreetMap Network. And this is authored by Jeff Boeing, who actually teaches at USC. So for all you guys who are from USC, you can actually take his class. He's teaching it right now. It's on urban data analytics or something in that regard. He's from the Seoul School of Price Policy, never get that right. And he's fantastic. He actually came, spoke to my class this week. And yeah, so he is not only a professor at USC, but he's also super active in the open source community, contributing this module that he wrote during his dissertation writing years, because he was frustrated by Esri and its lack of being able to do what he wanted to do. So he said, you know what, I'm just going to build my own tool, which is exactly what it did. And this is the power of the community that is open source. He wrote this module for his own research and then realized that, you know what, if it was useful for my research, it's got to be useful for other people. He put it out there on GitHub, and then it all of a sudden is used by tens of thousands of people. And what the OSMNX library does, it allows you to query and import data from OpenStreetMap anywhere in the world. It's super powerful. And you can bring in buildings, parks, cafes, points of interest, but it's the real power, and the reason he wrote this tool is more for its network capabilities of producing network graphs based on street segments and nodes. We're not going to get into the intricacies of kind of street network graphing, but instead it's an introduction to his tool, his module. And I'm glad to bring it up because, you know, we're at the Mapathon with USC and UCLA. So it's very timely to be able to use a kind of a homegrown tool. Okay. Let me go back. Yeah, and the last library we're going to use is a simple library called Contextilly, which is kind of a mapping module that allows you to bring in base maps into your plots. We're going to create plots, and it's always great to have some reference, and these base maps you can just kind of bring in as a background image to your plots. Okay, so that's the introduction to the Python libraries that we'll be using. I know you guys are eager to get started, But let me just make a few points about how you can actually query for OpenStreetMap data. Using the library that Jeff wrote, OSMNX, you can query by a bounding box. If you know the latitude and longitude coordinates of the area that you're working with, you can specify lat longs. It geocodes for you. So if you know an address, you can specify an address and a distance. Or you can actually just feed in Paris or Tokyo or Hong Kong. And then it'll get data for that location. One thing I wanted to make sure you understand is that this is potentially a dangerous interaction, because if you just say Paris and you don't specify a boundary, you could bring in a gigabyte of data, which will overwhelm your system. So for this workshop, I'm putting limits of 1,000 meters in terms of the radius of area that we're going to cover, so that we don't overwhelm our browser and our system. Okay, any questions before we actually start the interactive component? Are we all good? And everybody's on pace here? All right, the silence is beautiful, great. Okay, so let's start. The first interactive cell that we have here is this one that says, it's titled Import the Libraries. These are the 4 libraries that I just spoke about. And in Python, this is the syntax to import external libraries to bring into your notebook. So import OSMNX, notice the as OX, this is an alias so that we don't have to type in a lot more characters. Pandas is typically aliased as PD. GeoPandas is, the convention is GPD, contextually CTX. Okay, so we're gonna bring this in, highlight this cell. You should see the blue bounding box around it, and then do a Shift Enter. And then you should then see an asterisk temporarily on this square bracket in here, and then a number should show up. The number, right now it says number 1, indicates that this is the first cell that you have run in your notebook. And this number, if I run this cell again, just because I want to, I can do a Shift Enter on it and notice that the number is now number 2. So it's just an indicator of the sequence by which you ran this cell. Okay. So I'm going to go to the next interactive cell, and we're going to define an area of interest. I'm going to allow you to change this in a bit. But for the sake of consistency and making sure that we can all kind of produce the same results for now, let's not change this and keep it to Santa Monica. So address is equal to Santa Monica. I'm going to do a Shift Enter, and now I have a number 3. Maybe most of you have a number 2 there. It means this cell ran. And this is Python code to say, hey, let's create a variable and let's call it address. And then what is address? Well, address is, we're defining it. Address is Santa Monica, Los Angeles, California. Okay. So we're creating a string variable called address. It has no other power than holding a set of a string characters of Santa Monica, LA, California. All right. Moving on. The next cell, which begins with %% time. %% time is a kind of they're called magic commands. This is a Python command simply to say, I want to know how long it took this cell to run. So it just outputs, it just lets you know, especially when you're running a Python command that you know might take time. It's a good indicator to see, oh, it took 10 seconds to run this cell, or it took 20 minutes. Hopefully not. But let me explain what's going on here. So first of all, I just want to know how long this cell will take to run. You guys can go ahead and run it, but let me explain it while you're running it. I'm defining a new variable, OSM. And I'm saying, what is OSM? OSM is equal to, and then there's a whole bunch of code here. The geometries from address command here comes from OX. What is OX? OX is, remember, the alias for OSMNX. So this is a command that exists in the Jeff Boeing's library that allows us to interact with OSMNX. And he has created a whole bunch of commands, of which one of them is, hey, get geometries from address, which means that feed it an address and then bring us back the geometries from OpenStreetMap. I'm also saying what I want it to give me back by providing a tag. And in this case, since we're bringing in buildings, I'm saying, hey, I want you to bring me in buildings from the address that I provided. What is address? Address is Santa Monica because we defined address to be Santa Monica. And I want you to only give me buildings within 1,000-meter square area. This is really important because if you don't specify a limit, it's going to try to get every building in Santa Monica, which could overwhelm your system. So go ahead and run this. I think this should take about 20 seconds or so. What are the times that you're getting? Oh, it took me 8 seconds. Okay, it's not bad. 1.8, is that wall time or CPU time? 15, 9, 11. Okay, so so it's not bad, right? 10 seconds isn't too bad in terms of bringing in thousands of buildings into your notebook, which is what it did. Well, let's find out exactly how many. So I have this warning about just being careful about bringing in buildings. Buildings are polygons, so they're actually pretty heavy. And now let's kind of do a little data exploration. So we brought in all these buildings and we put it in a variable called OSM. Now OSM is well, we're going to find out what it is. The first command I want you to run is osm.shape. So when I run osm.shape, it basically tells me what are the dimensions of this OSM variable that you just created. And it's just a tuple of two numbers, 4,000 by 58. So that means there are 4,025 rows, 58 columns. That's what shape tells us. Other kind of commands that you can run is what's the data type? So we created OSM, geometries from address. I want to know what the data type is. And it spits out, oh, it's a GeoPandas geodata frame. What this tells me, since we also imported the GeoPandas library, it tells me that this is a data frame. That's what it's called. A data frame is like a data table based on the GeoPandas definition. And we know that GeoPandas is spatial. So this is a good sign. We brought in data from OpenStreetMap. The module from OSMNX defined that import as a geodata frame, which allows us to map it. Yes, OSMNX, the default measurement is indeed meters. Yeah. Yeah. Great question. Okay, so the next command, Python command we can run on a data frame is .info, which gives us information about the data that's in the data frame. So when I run this, you should get a result that looks like this. There's a lot of information going on that's produced by a simple command .info. Let me kind of break this down a little bit for you. First of all, it tells me how many entries there are. This is consistent with .shape, 4,025 entries. It starts from 0. A lot of coding languages and arrays, they start with 0 and not 1. So 0 to 4,024. So that's the kind of numerical index that it provides our rows. The data columns are 58 columns. And these are the columns that it brought in. All 58 of them are listed here. Notice also the additional information that .info gives us is how many of these columns are not null. So for unique ID, 4,025 are not null. What basically tells me there's a value in every cell for unique ID. When you see a column header that has fewer than 4,025, that tells you that, for these kind of fields here, it's almost entirely empty. They're almost like unnecessary, unusable in terms of if you wanted to do data analytics. And the last thing I want you to notice is the data type. So for every column, what's the data type? Object. Text and string are typically in a data frame they're given a data type of object. So for the most part, when you see object, you can think of them as strings. The geometry column is very important. This is what makes it a geodata frame. The geometry column tells me that it comes with the capacity to map this information. The geometry column is chock full of coordinates for these polygons. So that's just kind of a snapshot view of the data and what it's made out of. But let's actually look at some rows. And again, the Python command to get a preview of our data is osm.head with parentheses in them. And if I run this, it gives me the first 5 rows of our data. So this is what the data looks like. And you can see all these null values you can see on the right here, which means we probably can't use these columns. And this is what the data looks like. You can also run a different command. If you wanted to see the last 5 rows of a table, it's .tail instead of .head. This is now the last 5 rows. You see the index here, 4024. These are the last 5 rows in our data. Or you might, this is my favorite command, is the sample command, osm.sample. Sample gives me, and I put a 10 in there. I want you to give me 10 random rows. I love this command because, you know, it's not the first 5, it's not the last 5, it's 10 random rows. So if you wanted to do a kind of a check of your data, the sample command is pretty cool. And moving on, eliminating unnecessary columns. This is a practice that you will do a lot when you bring in data from a foreign source. And then you're kind of viewing it and exploring it. And you're like, you know what? I don't need 80% of the columns here. Let's trim it down. So let's trim down our data frame that has 58 columns. So to get a list of columns, we kind of did it with .info, but this is a way to put it in a list. If you wanted to see them in a list, here they are. This is a command list and then the data frame in it. You can also, well, this is the same command just to double check. .info gets us a list of all the columns. And really, what we really need for this exercise is 2 columns. It really boils down to that. You will look at the data and you're like, you know what? I really only need 2 columns. The 2 columns I want to keep are the geometry column. So I'm creating a new variable and creating a Python list. A list starts with a square bracket, it ends with a square bracket, and it's separated out values with commas. So we're creating a Python list, and I'm only keeping 2 columns, geometry and building. I'm going to go back to that .info to tell you where I got this value from. So building, since we imported building, this is one of the key columns that are important in order for us to map it. So if I look at the preview, where's my preview here? Building tells us what the building type is. You see my random set. It's either an apartment, a house. There's probably other types here. And the geometry column, which isn't listed here, that's the one that allows us to map it. So we can't eliminate the geometry column. Okay, so we're going to keep 2 rows, just 2 columns out of the 58. I create a variable that says these are the 2 columns I want to keep. And this is the really nifty syntax in Python to kind of redefine our data frame. So I'm saying OSM, we'll redefine OSM to be OSM, but with only the columns I want to keep. Hopefully that makes sense, which are the 2 columns, geometry and building. So then once you kind of overwrite the original one with only the columns you want to keep and you run this, it should be a lot slimmer. And now it eliminated 56 columns, which is fine by me because I really didn't need those columns. If I need them again, I can re-import the data. But for the purposes of this exercise and to keep it clean, I like to trim my data. So now we have the geometry column and the building. Look at that geometry column. You can see it defines it as a polygon, and then it has a whole set of coordinates that indicate what the vertices for every point in that polygon. Okay, so let's play with this data a little bit. Let's make a chart. Before we make a map, let's kind of explore this data a little bit more. So counting unique buildings was probably something that you were thinking about in Santa Monica. How many buildings by building types do we have? And there's a nice command in Python, value_counts. So for any given column in your data, you can apply value counts, and it outputs a result of unique categories within that data and a count for that value. So I'm going to create a brand new variable, and I'm going to call it OSM building counts. And then what it's doing is it's saying, okay, OSM is our database. Building is the column. So we're chaining commands here. So OSM is the data frame, building is the column, and I'm applying value counts to that column. Starting to make sense in terms of Python and how you kind of chain commands one after the other. And then let's output the results from here. And this pretty quickly goes through 4,000 records, and it does a distinct count for, it's like a pivot table in Excel, if you've done pivot tables, and it outputs, tells me, okay, house is the highest count within Santa Monica, apartments is second at 1,300, residential, and so forth. Now, these categories are defined by the authors of OpenStreetMap, which could be you. You'll notice there's one called yes, and yes isn't a building type, but yes happens to be the default. If you don't specify a building type, for whatever reason, OpenStreetMap returns yes as a building type. All the buildings that we digitized yesterday and today, this morning, some of you for our Mapathon, because we only categorized it as building, they're going to return yes. So that's just the way in terms of the data that it brings back. You can maybe rename this to be uncategorized or something like that. All right, so let's create a data frame of the value count so that we can create a chart for it. Right now, the result, and let me tell you the type, OSM building counts, it returns something called a series. Okay, a series is not a data frame, and it's difficult to chart a series, and it's easier conceptually to think of, oh, I have a data frame, which is an equivalent of like an Excel table that I can then produce a chart from. So right now we have a series, which is a one-dimensional kind of an array of values. So we're going to convert OSM building counts into a pandas data frame. And again, the command is here, PD, remember that was the alias for pandas, data frame. I want to create a data frame for pandas on the OSM building counts. And I'm going to define it as a new variable called data frame OSM building types. And now when I run this cell, it looks similar, but it's kind of structured a little bit more like a table now rather than a list. But we're not done yet. Because the data frame, if you look at this data frame, it created, this column does not have a header, right? And that is because in Python, in pandas, a data frame includes something called an index. And the index, usually it's numeric, but it doesn't have to be, is the one that's not labeled. So in this case, the index has become the building type. So we want to fix that a little bit. So in order to fix the index, we need to run a command to reset the index. So now we have the data frame, we're resetting the index, and we're redefining the data frame. And if I run this, you'll notice that now we have a numeric index on the left, which is better for a data frame. And then we have the original index, which is here. and then the count. By resetting the index, we've created a new index. And the final step before we go into charting is that we want to rename these columns. So notice that the columns are right now index and building. This should actually be building type. And where it's now building should now be count. So renaming columns in Python for a data frame is actually, once you understand it, pretty simple. Because you have to define so here's my data frame, dot columns, and you just feed it the column names that you want it to be. Does that make sense? So in a list, I say I want the first column to be building type and the second column to be count. And that's all I do. I just say dot columns, and here's a list of the column headers. And once I do that, you'll notice that my result, here's the index, has no header. It's just the index, the numeric index. Now we have the building types in its own column, and we have a count as its column as well. Okay. All right, everybody with me so far? I'm gonna kind of have you guys run this on your own in about a second, but just wanna make sure that everyone's doing well. Can we name it building type and not building type? Yes, Yash, you can. It is typically recommended that you don't have spaces in your column headers. It's not that you can't, but you could run into syntactical problems later on if you have a space in there. In that case, I would use a camel case. So I would do building, no space, capital T, building type. But yeah, you can. You can have spaces if you wanted to, but it might cause problems later on. Okay. All right, so let's create a chart. Let's plot it to see what happens. If we just take our data frame and then just run a plot command, which is a pandas command, and see what happens. So just by default, it produces this plot. That's pretty cool. Just one line of code and it actually produced something. Do you guys know what's going on? What did it do? What's in the X? What's in the Y? Any thoughts about this? The Y is the count. Excellent. Yeah, those numbers indicate a count. And the X is the building type. Kind of. It is actually. The X is actually the index, right? So what it does is since you didn't give it any arguments, you didn't specify this is what I want in the X and this is what I want in the Y, it makes assumptions for you. First of all, it just defaults to a line plot. And then it says, oh, for the X, I'm going to use the index. And for the Y, I'm going to find the first numerical value column. So that's why it's able to produce a plot. But we can add additional arguments to make the plot make more sense. So for example, instead of just a simple line plot, we can specify what kind of plot we want by saying, I want a horizontal bar, bar H. And then I want it to be larger, which is fig size, width, and height, 12 and 6. And I want to actually specify X not to be the index, but I want it to be building type. And if we run this with a bit more commands in it, you should get a chart that kind of makes a little bit more sense. Okay. And just to let you know, there's different kinds of plots. If you take the bar H, the H away from here, and I run this again, it's a, it's a vertical bar, a more traditional vertical bar than the horizontal bar. So you can start to see the kinds of manipulations that you can do in your code to do this. The height values, that's a good question. It's definitely not pixels. I don't know what the unit of measurement is. It almost feels, you're right, it almost feels like it's centimeters, but I don't know how centimeters converts to pixel space. I'll have to look that one up, unless somebody else can answer that question. what unit of measurement is the fig size in. Okay, so sorting a data frame, you'll notice that right now, the largest value is in the bottom. So I just want to quickly go over sorting in pandas. When you have a data frame, you can sort the data frame differently by applying sort values command. And the way you do it is you get your data frame. Again, you're chaining commands. So you say dot sort values. The argument that you need to feed it is what column do you want to sort it by? So in this case, I want to sort it by count. And you can set the sort either be ascending, true, or false. So when I run this, it redefines the data frame, but now the order is reversed. And so you can understand how this could be, meaningful to get the top 10 of something in your data that might have many columns. Once you sort it, I can then run the plot again. And this time it's reverse order, which makes a little bit more sense if I'm going to publish this results to have the top values being the top of my horizontal bar. So here's the results of that. Okay. All right, I'm going to take a quick little break here and allow you, let's have 10 minutes for you to both take a break. And actually what I want you to do is go all the way to the top of the notebook, enter a location of your choice right here. So where is it? Okay, right here, address. Change this anywhere in the world. And then run the notebook from top to bottom until you get that, not to the bottom, until you get that bar chart. Okay, so you can type in, Bangkok. I don't know if it'll produce anything, or a location anywhere in the world, and produce a bar chart. And what I want you to do when you produce that chart is there's a link to a Google Doc here. If you could, once you produce the chart, enter your name. So I'm going to say Yoh and paste your chart in there. So I'm going to right click and copy my chart for Santa Monica and paste it in here. Okay. So I want to have a running document, a gallery of charts that you guys are producing. So let's do this until like a little past 10 before we move on. So hopefully we'll get to see building types from different locations in the world pop in this document. And let me know if you have any questions or put it in the chat. I see that Ben has answered the measurement question. The Google Doc link is in the blue cell down here. There's a link to the Google Doc. So find that blue cell in the Jupyter Notebook, and there should be a link to the Google document. Okay. Let's see. Question about.
So Yo, I also made a binder link. If there is anybody else on here who isn't from UCLA or USC,
Oh, great.
you can go to the link that I'm going to paste into the chat.
Thanks, Ben.
Mhm.
Okay. There's Tokyo, Santa Monica, Folsom, California. Atwater Village. Nice. Cincinnati. Of course.
How do we get to the Google Doc again?
The Google Doc is in the blue cell here. So in your notebook, right below the kind of the plot that you created, there's a blue cell. And the link should be in that cell.
Okay, thank you.
Sure. Madrid. Nice. Oh, we got two. Two from Spain. Some of the buildings are points, and that's a good question. Yeah, it's just a matter of what OpenStreetMap returns to us, isn't it? And sometimes you're right. When you ask it to return buildings, some are actually categorized. It's based on the categorization. So if you entered a building as a point, it may return points to you. I haven't actually seen that happen, but it sounds like you did. You can either filter out to just be polygons, or maybe it doesn't matter. Maybe you can visualize it as points as well. Redondo Beach. Downtown LA, a lot of retail. Yep. Now this is fantastic. All right, we're gonna move on into kind of something more fun, because we're gonna now create some maps based on our locations. So this is great. I'm gonna stick with Tokyo. Again, the yes basically means that for that particular location, buildings just haven't been categorized other than just being tagged as buildings. And that is in itself a shortcoming of this particular data collected from OpenStreetMap for that type of data. But in other locations, and mostly in Los Angeles, most buildings have been tagged by their building type. So certain locations, this analysis might work better than others. Okay, let's move on to GeoPandas. I'm going back in my presentation mode here. So GeoPandas, so we've been working kind of in the pandas world, which is more about data exploration, data manipulation, querying, filtering, and visualizing plots. GeoPandas does all the same stuff, but more kind of in a spatial sense. So we're gonna, first of all, go back, not to our building type data frames that we kind of created, go back to the OSM data frame that we started out with. So just to double check, if you do a type OSM, even if you reran your queries with Madrid and downtown LA and all these different locations, the type for OSM should still be geodata frame, because that's what we downloaded from OpenStreetMaps. Now, if we just plot it, and you just say OSM.plot, and I'm giving it a fixed size, this time I'm putting it into a variable, because we're going to manipulate this plot after we create it. So it's just a way to make sure that we're capturing the plot in a variable. If I run this cell, then, ooh, okay, that's the Tokyo cell. I'm just put it in the middle. So you should see a different plot depending on what you searched for. So this is my Tokyo plot. I think this is around, I think that's Tokyo Station actually. That's my guess. Because all these little slivers here, I believe, are platforms for all the different, because this is the equivalent of Union Station in Tokyo. And these are all the train lines that come into Tokyo, including the bullet train. So there's my plot. And if you wanted, and this is kind of a nifty little thing, you want to check your data, you can do remember the sample? You can do a random plot for a random building. So if I run this, it just gives me the outline of a random plot. I can run this again and again because it's fun and get me just kind of a random sampling of buildings in my data frame. You can increase this and say, hey, plot me 10 plots. But since it's random, it's kind of spread it out all over the place. But it's just kind of a fun exercise, just kind of to get a feel about what kinds of building shapes there are in whatever location you searched for. But we want to color code. We want the map to be a little bit more meaningful and produce some kind of results that we can publish. There's a column argument and CMAP argument, and it's kind of explained a little bit here. But let's, hold on a second. Color coding, CMAP, yeah. Let's do a bunch of things to this map to clean it up and color it at the same time. So the first thing we can do, I think actually this might be out of order. Let's see, 4.2. Okay. Yeah, I think I missed an explanatory cell, but we're going to do to our plot, we're going to create a legend, and we're going to learn how to move that legend out of the way and add a title and remove the axis. So you notice that every plot that you create has these axes that represent latitude and longitude coordinates. But if we're going to publish a map, we don't need that. So this next kind of cell block here does a lot of things. We're adding so many more arguments to make our plot more publishable. So let me just go over a few things. We've done the fig size. We're adding column, and column is what we want to categorize our map with. And we have the building column. So what the plot does is it goes through and colors every building differently based on the building type. You can give it color code, and with a CMAP, we give it what's called a color map, and there are predefined variables that you can use to define what kind of colors you want to populate it with. We want to add a legend, so there's an argument for legend, make it true. And the legend keywords is just where you want to locate the legend, how you want to display the legend. I've also set it so that there's no border around the legend. And then we give it a title and we set the axis to be off. A lot of things happening here. And then when I run it, you should get a plot that looks like this. Okay, so I know there was a lot to unpack there, but oh, I see a point actually here. Someone mentioned that some of the buildings are a point type. So I see a bunch of points here as well. But let me pause here, make sure everybody is in the same page here. And hopefully you understand, at least, you know, if you're new to Python, there's a lot to unpack here, but hopefully you at least conceptually get what's going on in terms of, okay, there's a command to plot, there's a parentheses inside plot, and you can feed it a whole bunch of arguments that define what your plot will look like. In this case, this is a GeoPandas plot. You have to give it a column in order to color it, a color code that defines the colors, and whether or not you want the legend or not. Notice too, the title. So there's a set title argument, and I have hard-coded building types in space, and then I close a single quote, and then I have concatenated a variable in the title. So whatever you define for address gets plugged into the title. Does that make sense? So it's kind of a cool way to include within the title a variable that you've defined earlier on. All right. Finally, we can add a base map. In the very beginning of this workshop, you might remember I mentioned another library we imported. It was called Contextilly. And this library allows you to produce a base map. So when you, and there's a couple of things, and we get into a little bit of GIS here. Base maps for the web are typically kind of pre-baked imagery for all the different zoom levels that exist in a web map. And since they're pre-baked, in other words, they're images that have been created at a particular coordinate system, we have to adjust our maps to fit the coordinate system that the base maps are made in. And it's a standard for base map tiles to be created in something called a Web Mercator coordinate system. So what we have to do with our data, our OSM data, is we have to convert our OSM data and reproject it to the same projection that the tiles will be coming in, the base map, which happens to be Web Mercator, and the code for Web Mercator is 3857. So this little cell here, what it does is it reprojects our data to the same projection system that the base maps are at. And this is a necessary step. Otherwise, our buildings will be plotted in outer space or something. So make sure you reproject your data. And now I've defined a new variable for the data that's OSM Web Mercator, and then run the exact same thing with the Web Mercator data frame. And then see in the bottom here, here's the code. CTX is shortcut alias for Contextilly. Add base map is the argument to add a base map. And then this is a syntax based on their documentation on how to add a base map to your plot. So once I run this, I should get a darkish base map here. There we go. Okay. So whether or not you like this plot better, I kind of like the white plot better. You can also change the base map. I just happen to choose a dark base map. But for example, if I choose the OpenStreetMap data, I've provided it here, commented it out. You can uncomment this and comment the dark matter one and rerun the cell. And this provides a different base map. the problem with OpenStreetMap is it's very colorful. So since we're coloring our buildings a certain way, if you use OpenStreetMap, they get blended in and it's hard to tell anything from the map. So that's why it's better to choose a dark or light base map for what you're trying to do. Okay. So are we good? I'm going to pause again and let everyone catch up. If you could, if you've produced a nice little map, go back to the Google document. I'm going to choose my white one because I like my white one. I'm going to copy this image. Go back to the Google document and paste it under the bar chart that you pasted in earlier. Okay, so delete that. Okay. Are we doing good? Any questions so far?
Yes. Yeah, I have one quick question.
Sure, Andrew.
The issue with the light colored maps with our building footprint colors,
Yeah.
could we put like a dark border around the building footprints to kind of have them pop on that light color map more?
That's a good question. I'm pretty positive you can. I don't know off the top of my head what the argument would be. It would definitely be somewhere when you plot it, but I'd have to look that up because there's, you can set transparencies, colors, and so forth. But yeah, sorry, I don't know it off the top of my head, but I can look that up later. Write it down. And you're right, there's so many different strategies on how to make your map stand out. There's visual hierarchy in terms of, what's important for people to latch on the moment they see your map. Sometimes you don't need a base map if what you're trying to inform is urban form and not necessarily the base map's not important. There are studies about, building footprints from all over the world, how condensed they are. And you can have like a facade of, maps from all over the world that kind of inform the history of space and how, building types are designed in different areas of the world. So let's see if we can actually start to see that here. Oh, that's great. That's Jesus. Great. Wholesome. Look at that. Where is this? Oh, Redondo Beach. That's beautiful. Looks like a stadium, huh? Well, actually, that's USC. No, that should be, I think that's Redondo Beach. Yeah.
Yeah, my title got messed up.
Your title got messed up. Okay. That is Redondo Beach, right? I see kind of a ocean front there. Wow, look at that. And understand that since the distance parameter for all these plots are consistent, so all these maps are at the exact same scale, just centered in a different place in the world. So you can just visually see what areas have bigger building footprints, which areas are more condensed and clustered or dispersed. And the color differentiation is also very telling. Wow, look at that. It's almost like a painting. That's beautiful. That just kind of tells you about a history of place right there, and how certain these areas are probably deep in entrenched in historical kind of urban form. It's not gridded. That's fantastic. Downtown LA. Look at that. Yeah, there's that whole retail corridor right there. All the factories just east, west of downtown. Fantastic. And look at that, Palm Springs, Riverside. Yeah, that's interesting. All these houses in the Palm Spring are points. They've been designated as points. I wonder if that's a new development there. Not sure what's going on there. Austin, Texas. Grand Forks. What's going on there? It's interesting. Oh my gosh. Okay, who put in Banda Aceh? Julia? Well, are you from Indonesia, Julia?
I lived in Banda Aceh for 2 years, but I'm not from there.
Oh, no kidding. I was there in 2005.
After the tsunami.
Yeah, in March of 2005. So the entire city was gone when I visited Banda Aceh.
Yeah, it's all very new now because of all the rebuilding.
Do you know what area of, where's the, because it's in the tip of the Sumatra, right? So the ocean is probably, I don't know where, surrounding it somehow.
Yeah, I can't pinpoint this, but you can see this a big
The
road.
mosque, that's the mosque right there, right?
There are a lot of mosques. That
Oh.
might be the.
I wonder if that's the, sorry, it's getting into my own kind of interest, but the mosque was so symbolic because it was the lone structure really that survived the tsunami. So in the city that got completely washed away, the waves actually stopped at the mosque, which was a very spiritual moment and symbolic for the city that's largely Islamic. Wow, phenomenal. Well, I'm open to kind of either pausing here and kind of taking a break until our next workshop, or I can go over how to create a function. I don't know if that's of interest to you. We still do have about half an hour, but just want to know if you guys want to do a little bit more, you're a little exhausted, we can pause and do a little bit more mapathoning. But what is the mood here right now? And what are your thoughts about what we've produced so far? Okay, great. Are you okay? Great. I hope this document, and I hope you guys don't mind. I'm going to publish this on our website as just phenomenal work that you guys are doing. It's beautiful, it's informative, it's powerful, and just in an hour. I mean, we just did all this. We built a world gallery of building footprints in just an hour, using tools that many of you have never used before. So how can you, Craig, can you elaborate a little bit more? What do you have in mind with that question? How can you layer in notes about each object? Are you wanting the plot to be interactive so that when you click on it, it might show some details? Yeah, no, yeah, that's a great question. The plots that we've been working in our notebook, these are GeoPandas plots or pandas plots, the charts that are not interactive. So what it basically does, when you send this command, it goes into something called the kernel, which is a computer that does all the computation, not on your browser, but on the Jupyter Hub. And it says, oh, you're using Python, you're asking for this and these coordinates, you gave me the data, you want me to color it. It does all this computation in the kernel, in the Python kernel, and then it spits out an image. So that's why you can right click on this and copy the image, save the image. If you want to publish it in a report, that's what you would do. Python can also produce interactive maps. I don't cover it in this workshop, but you can use Folium, which is an interactive let's see, there's a quick start here. So Folium, you can actually build interactive plots within your Jupyter notebook. And you know, it does the same kind of thing. You can change the base map. So here's kind of OpenStreetMap base map. This is a Stamen toner map. And you can have these kind of points here. And this is where you could have an individual interaction with any of the objects that you produce. Now, as cool as a Folium map is, it's entirely JavaScript based. So when we have 4,000 buildings and we try to plot it on an interactive JavaScript map, the map immediately overwhelms the map will immediately overwhelm your notebook and your browser. So you have to kind of use it with caution. Maybe filter your data considerably down to maybe 1,000 objects before you use a Folium map. But it's also it's pretty awesome. You can see the documentation here and the types of things that you can do with your data. All within a Jupyter notebook. Pretty cool stuff. Okay, let's move on to something a little bit more advanced per se, because we're gonna get into a function. And I introduce functions in this workshop because when you build, you know, everything that we've done so far, so many steps, so much involved to produce a single plot. But what if you wanted to run the same thing over and over again for a different address? You'd have to go all the way back up, change the address, come all the way back down, run every cell again and again and again, and then you get a new plot. That's very inefficient, especially if you're doing like, hey, I want to run this on 100 cities. How do I do that? So what I want to do is kind of tell you how to build a function. If you've coded before, you're familiar with the concept of a function being, it's a set of code that you kind of package into what's called a function, so that when you run the function, it runs all the steps that you tell that function to do, and then produces an output. So what we're going to do in this function is, or what's already listed out here, is we're going to take everything that we've done and pack it into a function so that all we have to do to run and create a map is to feed it an address. Does that kind of make sense? But let's kind of think a little bit about what a function is first. So I have a little space, a cell here before we kind of talk about the big function. And let me run through how you create a Python function. And type along with me if you'd like. So the first thing in a Python function is you have to define it by DEF. So that's how you begin a Python function. So I begin a function, and then you can name your function whatever you want it to be. So let's just say, oh, I'm going to call it what country, just because that's what I'm going to call my function. Okay, and then you have a parentheses, and then you end your function with a colon. So that's how you end a function definition. And then you hit enter, and you'll notice after you type a colon and you hit enter in a Python cell that it's indented. So you notice how this is indented? So everything from this point on that's indented is part of this function. That's how Python recognizes that you're still within coding for this function. So let's just do something really simple. I'm going to do, sorry, that's in the way. Hello. So I'm just going to print hello, and I'm going to end my function. So now I've created a function that's called what country, parentheses. And then what this function does is simply it prints hello. So if I run this function, how do you run a function? You just call it country, right? What country? And I call it. And if I run this cell, what does it do? It spits out whatever I told it to do. So I said print hello. If I said print hello world, and I run this function, it will print hello world. So hopefully that's kind of making sense. This is how you start a function. And this is how you call the function. So everything we've been doing so far, you notice OSM.plot, and then it has all these arguments. Essentially, somebody wrote def.plot and then created a whole bunch of arguments. So let's take this a little bit further. If you typed in def, what country, and I can actually feed it an argument. So let's actually say, hey, in order to run this function, you have to provide it a country. So I'm saying, okay, it requires an argument for country. And then I'm going to change what it prints out. I am from space. And I'm going to say plus, so I'm going to concatenate in my output country. And country is whatever you feed it, because I say country is what's put into parentheses, and I'm going to output what you fed into country in this statement here. Now, if I run this, what country, it's going to produce an error because it says, oh, it's missing an argument, country. So now the function is smart. It knows that you have to provide it an argument. So here, I have to actually give it an argument. And I'm going to say, what country? Japan. And if I run this, now it produces an output. I am from Japan. Okay, so does that make sense? Can I have a confirmation before I move on? Good. Okay, thank you, Andrew. Great. Good, good. Okay. Now this is, it's kind of simple, but it's kind of important, and syntactically, initially, it may not make that much sense, but I think compared to other programming languages, Python is as easy as can be in terms of readability. So once again, define a function, give it a name, give it an argument, and do something with that function. So now that we've kind of, and there's, for example, I can provide a value here. And I can say, for example, USA. What this does, by actually defining what country is inside the parentheses of your function, it gives it a default value. So now if I don't have the, you know, just empty, remember we did dot plot and no arguments. Now this won't give me an error because what I said is if you don't provide country, give it a default value of USA. So I'm from USA. But I can override default by actually giving it an argument. And this overrides the default and says I'm from Japan. You know, if you have multiple arguments, you're going to have to actually define what it is that you're feeding it. So this is where you actually say country equals Japan, because you might have multiple arguments. So hopefully that makes sense in terms of the building steps of how to create a function in Python. Let's take this a lot further, okay? Now this is super advanced because this is a pretty sophisticated function here, but hopefully it'll make sense. Okay, so create the function, define it, give it a name. So I'm gonna name it something more specific. Make building map. No spaces, a function cannot have spaces. So make sure you either use camel case or underscores, or just a one line text. And the only thing this function requires is a location. I chose the word location so that it doesn't overlap with address that we used earlier. And that's the only reason I changed it to locations, just so that there's a differentiation between the two variables. What does this do? First of all, it gets data from OSM. So OSM equals, remember, geometry from address. What location are we feeding it? We're feeding it that variable that we're requiring. So location is required to run this function. And then we're feeding it to the geometries from address. We're doing the same thing. We're bringing in buildings. We're giving it a distance of 1,000. We're reprojecting it, okay, to 3857. We are creating that map with the dot plot, figure size 1010, column is building, there's a C map, there's a legend, putting the legend on the right, setting a title, getting rid of the axis, and giving it the dark base map. All this is indented, meaning that all this is part of this function. Now, if I run this function, okay, I'm gonna run this, nothing happens because all I've done is I've defined a function, I haven't run it yet. So a function you can create a function, it remains dormant until you call it. Now we can call it, run the function. So again, I have my magic command here. I want to know how long this takes. Make building map is how you call it. And you feed it a single argument, which is the address or the location. This can be whatever you want it to be. You feel free to change this. Now, if I run this, it's probably take 10, 15 seconds to run because it's going back to OpenStreetMap, grabbing thousands of buildings around USC, and then bringing it back. Okay, so that's how you create a function in Python. This Python function does a lot. It creates this plot for us. But you can change this to whatever you want it to be. Yeah, Craig, that's a great question. Behind the scenes of running this code is what's called a geocoder. So there's Paris, that's beautiful. And the geocoder is, I actually have a link to it. If I just pause for a second here, all the way to the top here. OSMNX uses Nominatum, which is a kind of worldwide public geocoder. And a geocoder means basically it converts text to coordinates or places. And I have a link here that takes you to a website that basically tells you what it would return. So, you know, I put in Paris, France, and if I search it, well, first of all, it tells me whether it returns anything. So this is a good way for you to check whether or not what you plug into that search box or in your Python code will actually return the correct address. And sometimes it does, sometimes depending on the syntax of how you write your address, it will return a different place and so forth. The more specific you are, yeah, it may or may not return what you want. But this is what it's using in the back end, this nominatum public geocoder. Is there a way to find out the central point of location for where 1,000 distance is taken from? Yes, I'm wondering. I actually don't think I have the code for that in here. Yes, Jessica, I'm trying to think. There's a kind of like a max X and a min X and a max Y and min Y. I don't know the exact syntax of how to grab those, but there's commands to grab the kind of the range of your X-axis and the range of your Y-axis, and then you just have to divide those in, you know, in two. Does that make sense? I just don't happen to know the syntax for it. I'll have to look that up. But that's how I would get the center of your shape. Let me go back down. Okay, create a function. Okay, the last thing I'm going to cover is a loop. So the function is great, right? You can write one line of code and it produces this plot. I mean, that's pretty cool. You can start to understand now that if you wanted to create your own module, then, you know, someone would import the Jessica module, for example, in one line of code, and then they'd be able to run jessica.makeBuildMap, and then it will produce this, right? This is how this Python world works. Other people are writing these really cool functions that then produce these outputs with very minimal code. But I think the power of this would be if you had a long list of addresses, and I'm just listing two here. But if we created a list, and in Python, a list is square brackets, comma, separated values. So I'm just doing UCLA and USC in a single variable that's a list. And how simple is that? All we have to do now is run a loop for every value in this list. And the Python syntax, if you have a list, this is a syntax to run through every value of that list. So for address in address list, so for every address in this address list, run that function, make building map, feed it the address, and then run, and then loop through every value in that list. Now this is going to take a while because there's two addresses, and what it's doing is it's going to OpenStreetMap twice, once for UCLA, once for USC, and bring back all the buildings that surround each campus. So there we go with one line, two lines, I guess, of code. It produced two maps. Okay. Pretty cool? Yes? All right. Craig, what are some techniques for finding groups of people actively mapping certain parts of the world? I think that's kind of more of an OpenStreetMap question. I don't know if you attended Rachel's talk yesterday, but she had an incredible graphic. You know, OpenStreetMap's been around since 2014, I think. And she had a graphic, well, actually probably earlier, but she had a graphic that showed OpenStreetMaps in 2014. and then kind of a time lapse on how OpenStreetMaps has evolved over time. Because OpenStreetMap can tell how the world is getting filled up with data because that we produce because it's community based, and that allows you to know what areas of the world are being actively mapped. So Craig, I don't have an answer for you other than you might be able to figure that out through the kind of the development of OpenStreetMap data. Yeah, and yesterday's presentation, guys, is, did you get my email this morning? I provided a link to the recordings from yesterday. She comes in at about probably an hour into that presentation after James's talk. I highly recommend you guys to listen to her and listen to James. Actually, they were both exactly, Gigi. They, you know, James and Rachel were really awesome. If you want to know more about humanitarian mapping and the kind of relationship that OpenStreetMaps has had with the Red Cross and all the efforts that are going on around the world, they both really clarified that for us. Oh, great. Thanks, James. Great. That's all I have, guys. Really excited to hear that it seems to have been useful to you guys. Open to feedback. Feel free to unmute, show yourselves, chat.